Good afternoon and welcome to Radio Control. It's a beautiful October day, so remember to start cleaning out the barbecues as barbecue season is nearly among us. And joined with me today, I've got Ludwig Petters, who's going to be discussing his exciting research in the field of chemistry.
Hello, Martin. I'm happy to be here.
Nice to see you. Nice to see you. So, for the first question, I was wondering, could I have a bit of background information about Ludwig? What is the story of Ludwig Petters?
Well, I guess most of you can already hear by my funky accent. I'm from Germany. I am from one of the suburbs of Munich, so one of the bigger cities in Bavaria. I had a good childhood there, but then decided to do chemistry, which makes you're growing up doing chemistry studies, let's call it that. So I did my bachelor's and master's studies in Munich at the Technical University in Munich. And during my master's studies, I decided I wanted to start seeing the world a little bit more. So I spent one semester in Ireland. And in the end, I got up to do my PhD and decided to do my PhD here in New Zealand on the other side of the world, here at Messi. And I'm here for about 2 years now, so I'm quite familiar with everything now and kind of feel home here now. So basic information to me.
Wow, looks like we've got Mr. International here. So, could you explain to the audience the fundamentals of your research?
Oh, yeah, sure. I'm working with metal organic frameworks for catalysis here. So it's a lot of words a lot of you probably won't be familiar. So I probably start by explaining some of the words I'm using. One will be catalyst. Most of you know or at least have heard about catalysts, especially combined with cars and making cars cleaner. But catalysts, in principle, just reduce the energy that is needed for a reaction to happen. So it speeds up the reaction or makes a reaction possible. And itself, it's not consumed, so it's recyclable. So it goes through several processes and gets the reaction going. You and your body have a lot of catalysts. The catalysts of humans are enzymes, and chemists always like to be inspired by nature, so a lot of catalysts are inspired by enzymes. And yeah, that's one of the words I'm gonna use. The other one is asymmetric catalysis. So the precursor asymmetric, which kind of means you produce mirror images of molecules. It's kind of like your hands. They are structurally the same, but they are also mirror images. So their connections is the same, but they are not. You can't put them on top of each other, and you have the same picture. That's really important for chemistry as well, because a lot of pharmaceuticals rely on that. So this is really, really important. And the third word I'm going to use a lot is metal organic framework. It's a sponge-like material, so it's very porous. If you think about, to make a picture, so you can have it in your head. It's built out of two major components. One are metals. You can think of them like spheres like Play-Doh, and then linkers that are organic molecules. You can think about them as like toothpicks. And if you've seen a child play with Play-Doh and toothpicks, they usually make like spheres and connect them with their toothpicks and build like a structure with that. So think about it as you build a cube with the toothpicks and the corners, the Play-Doh, and you just continue building cubes onto that. So you have like a huge three-dimensional system, which has a lot of big holes. And we do that on a molecular scale. So use metal centers and linkers, which are organic molecules, as the toothpicks, and build like huge three-dimensional porous systems. Well, our toothpicks are far more complex, and you can use not only one of the linkers, you can use several like I do. So the systems is not as straightforward and like cubical as in this example, but you get the gist. And I'm kind of in my research combining all three of those words and doing Catalysis with my MOF, metal organic framework, and I'm trying to do asymmetric catalysis, so only produce one of the two mirror images of molecules. That's the basic idea.
Wow, that is definitely a lot of different things put together. So, could you maybe provide some more distinct examples of these different components?
Well, I don't want to go in too much detail because
just like something that people may have encountered in their daily lives.
In their daily lives.
Okay, maybe going a bit by there. Maybe something they might have come across, let's say, but not in their daily lives.
Yeah. Well, MOFs are a kind of more newer research field, or newer, it's like 20 years old, but in like the grand scheme of chemistry, it's kind of new, and it's more a labs-based research yet, even though there are some new applications coming up. For example, for carbon capture, as we have a startup here at Messi and that deals with carbon capture with metal organic frameworks. So in daily life, you won't run into a MOF, but you will definitely run into asymmetric molecules, so like mirror images, because like most pharmaceuticals you take, like painkillers and anti-nausea pills or whatever, they are only one of the two like mirror images of the molecules, and if you take the other one, you won't be feeling good afterwards. So,
ooh, can they be very severe, these mirror images?
Yes, they back in the 80s there was this anti-nausea pill, which caused a lot of birth defects. That's like the big bad example of chemistry, and like I usually don't really like to say this example, but that is one most people out there know, because it like shines a bad light on chemistry. But at that point, the chemists didn't know better. We know better now, so chemistry helps people, not harms them usually. But it can have very severe effects.
Well, I mean, it sounds like knowing this example highlights the importance of being able to separate the mirror images from one another.
Yes.
In some ways, I think it shows that it highlights the importance of chemistry rather than detracts from it and understanding it.
Well, it also shines a bad light on it, because, people taking in medicine and they getting harmed with that is always not a good thing.
Yeah, but it's important to learn from past mistakes, such as that.
It definitely is.
And I think people are much more aware of these mirror images. So, you made mention of being able to perform carbon capture with these metal organic frameworks.
Yes.
Perhaps you could go a bit more in detail about that.
Sure. I'm not working on this project, but this project is performed by colleagues in my research group, and they are using a MOF, metal organic framework, and as I mentioned, it's like very porous, so it has a lot of empty void in there. There's space, and some molecules stick better within this void than others. So if you have this MOF on air or like a gas stream, it's far more likely for CO2, so carbon dioxide, to absorb in the pores and a kind of stick in there. So they fill the pores up, and nitrogen, which is the component like the air is made out of mostly, doesn't absorb onto it, so it just passes through it. So in the end, you have a material which is highly filled with carbon dioxide, and air which has lost a lot of carbon dioxide. And well, you can use it as storage, but what we try to do is have like two columns and run them in like an industrial process where it's one absorbs and the other one desorbs, and then we use the carbon dioxide for some other chemistry. We are not dealing with that right now. We are more like focusing on to actually absorb it, like get the stuff to work. And yes, that's the idea behind that.
Sounds rather quite interesting. And you made mention, so you talked about the combination within your area, which was the metal organic frameworks for catalysis, for only the to separate between the mirror image
yes, exactly.
things. So could you maybe give an outline, now that we've like kind of gone through the basics, like a more of an outline to it as one picture?
Well, I didn't go in that much detail earlier. The cool idea about my project is, well, chemistry is able to do asymmetric catalysis quite good already. So they getting selectivities of the one hand of 99.9%. So it's really, really good. The selling point of my research is that metal organic frameworks are crystalline, so that it's a crystal, it's a solid. And most reactions in industry, so like pharmacy, it's mostly aimed to like pharmacy or basic reactions that are used there are in liquid. So the one major benefit of my catalyst is that you can just filter it off after you're done with the reaction and don't have to go through the hard process of like separating a liquid out of a liquid, which is one of the big selling points. And the other one is usually how chemists do it. They have their catalyst unit, so the part which speeds up the reaction, and their the information of which hand is produced, so the chiral bit, within one molecule. They are bound to each other, and it's really usually it takes a lot of effort to synthesize this chiral catalyst. So it takes weeks, sometimes like decades of research to get one good one for a reaction, but that one is really good usually. And we're trying to do something new by ripping this catalyst unit apart from the chiral information, so have them separated in the molecules, and we attach those separate parts to our individual building blocks of our metal organic framework. So the toothpicks, we use different toothpicks that are within our framework, and we attach the catalyst part to one of them and the chiral bit to the other one. And because of how our MOF is built, those parts attached to the linkers are within one of the open pores, so they are getting in close proximity to each other. And this is kind of similar to enzymes, where a lot of different amino acids that are on like a long strain getting folded and rolled up, and then form like an active site where they're close to each other. And we're doing the same with attaching them to our linkers, and the linkers always form the same pore, so it gets close to each other. And then we can perform actually the catalysis, and just because the surrounding is chiral, so the information of which hand is produced is in the surrounding, we get actually transfer of this information onto our product, which is completely new, never been shown in literature. So we are doing something new, which is the selling point of my research.
So in terms of comparison, like how expensive would the traditional catalysis be versus your one?
Well, my one is like it's it's not perfect yet. Like we can show that it works, and it's actually getting somewhere now. After hundreds and hundreds of hours in the lab and like a lot of failed experiments. That's just part of research.
I know.
I don't actually have like a perfect price comparison, but we use zinc as a metal, which is a very cheap metal compared to platinum or rhodium. And the organic molecules, well, it depends on what you have, because sometimes you need like 5 steps to synthesize them, sometimes only 2. And, well, it's just like adding up the hours, I guess.
So it does save time ultimately.
Oh, well, yes, because...
and time is money.
Oh, yes, it definitely does, because, as I mentioned, you attach on like one of the parts to one of the building blocks. So you can easily switch out the building blocks if you have like a library of that. So you want to do this direction today, so you add this building block with the catalyst which works for this direction. So you kind of like create a library of linkers you throw together, and like depending on what you want, you get it out. That's the idea behind it.
So you've basically got like a library of, well, you said linkers?
Linkers, yeah. Like
so the things connecting each of the nodes.
Yes, exactly.
And that will change what can be filtered through it. Or
not filtered, which direction we can perform. Which catalysis we do.
Which catalysis can be performed in it. So it's kind of like, like... in a very basic sense, like clipping together Legos.
Yes, exactly. That's the idea.
And when you've got this fully made out, like, so what are some of the examples that you're wanting to test first?
You mean which kind of reactions? Or
yeah, which kinds of reactions?
We created within our research group we call it internal handbook of reactions, because, well, we add a catalyst unit to one of our linkers, and then we want to see what is actually active for, because like designing a molecule and actually being able to use it the way we designed it, it's always like not always that straightforward. But we have this created this handbook of reactions based on literature which are just used in pharmacy. So like big reactions like aldol reaction, Henry reaction, those reactions have usually a name. And they are commonly used in pharmacy, in industry. So we try to focus on those that are actually useful. Yep. So we have make a bigger, stronger point for our catalyst. Because like the end goal of the whole research is, first of all, a high-level publication.
Yeah.
To like spread the news in the world that it's actually possible, and other research group will probably come up with some new ideas based on our invention, and hopefully down the line, like 20, 30, 40 years, it's standard in some reactions used in industry.
So it would be used to make new kinds of and existing kinds of pharmaceuticals.
Hopefully, yes.
What kind of pharmaceuticals do you think are good candidates for this process?
I haven't had a look into literature for that question. I'm sorry that I can't really answer this question, because right now my job is to make my catalyst actually work better than it was 2 months ago, and that's a lot of hours in the lab trying. We change one part in our catalyst, see the effect, think, okay, why do we see what we see, and then trying to design a new molecule to see a different effect, and get all the information about, well, how can we actually influence our catalysis?
Okay, so from what I've been hearing, is your group like the only group in the world working on this stuff right now?
On exactly this stuff, yes. We are working with a metal organic framework which was first found here at Messi. It was found in 2017, the one I'm working with right now, but like its precursor 2015. It was the first metal organic framework with 3 different linkers, so 3 different kinds of toothpicks. That was completely new, we work with this moth because it's fantastic. It's good. It's stable. We can because we have so many different building blocks, we can attach our 2 different parts. The pore environment is perfect for the idea we had. The whole project is kind of based on an invention 2015.
So you made mention that it's got 3. So it was new that it had 3 different kinds of linkers.
Yes.
Is that because like each linker is different, or because there's 3 of them, or?
Well, the first moth had 1 linker.
Yeah.
It's always the same like size toothpick. It's just always the same. Then it got more complex by using 2, and if I say 2, the linkers have to be chemically distinct, so they are not interchangeable within the structure of our moth. So they need to have a different length or a different connectivity. Usually those molecules are linear, so they are symmetrically and have like 2 points where it can attach like 2 ends of a toothpick. But for example, we use 2 like linear toothpicks, a small and a long one, and one which has a connectivity of 3, so kind of like a star-like.
Mm. And so when you've got more of these linkers, does it like change the geometry so you get more dimensions?
Yes, exactly. So it's not straightforward that it just forms like cubes, but there are like hundreds of possibilities like how the pore can look like. But the thing is, because it's very like crystalline, it's very ordered, meaning it's always building the like getting together in the same structure. And the problem with like having that many variables in the system is you add a little bit more of one linker and you get a completely different structure, because the concentration of the one is higher than the other, and now it's more likely to attach in this way. So it can be a very tedious process to figure out the perfect conditions, but in the end you get there.
So I suppose it creates like a greater list of possible combinations of that can form like a very wide variety of metal organic frameworks.
Yes, exactly.
Do you think that it's possible in future to have 4 linkers?
Probably, yeah. Yeah, why not? Like, there's gonna be a lot of trial and errors, but it's science. It evolves over the years, and like you will always end up with more complex stuff.
So, so you said that only your group is specifically working on, doing the catalysis for the mirror image things with metal organic frameworks. Are there also some other like groups that you work with that might be also working with these metal organic frameworks in a slightly different fashion?
I have to rephrase that, because like there were definitely groups out there that are doing mirror image catalysis with moths, but they are like all the publications so far always have been based on the principle that the chiral information and the catalyst unit are within one molecule. So they would be on one of the linkers. So they are still connected in one molecule, and we doing this new principle where we kind of rip them apart and have them on different linkers, and that has not been published. Maybe out there in the world there is a research group which does exactly what we do, but they haven't published it yet. So it's kind of a race.
A race to who can get information out the fastest.
Yes, exactly.
But in the end, I suppose everyone kind of wins.
Oh, well, yeah.
Well, maybe, but not so much for you if you wanted to be first.
Yeah, sure, no.
But I meant as the world as a whole probably wins. So, what's like the community like in the medical? Why do I keep saying medical? Metal organic framework space. Are there like large events targeted in this area?
Yes, there are conferences around that, and like complete metal organic framework schools. So this research is ever growing. Like the number of publications each year just increases dramatically. Back in Munich, I already worked in a research group working with metal organic frameworks. That's where I got the taste for them. I was not able to do that during my master studies because, well, the pandemic hit and we were not sure how much time I actually can spend in a lab. You know the story. It's like the whole world was chaos, kind of, or like not chaos, but everything was so uncertain. So I worked with something kind of related, kind of not. But using the same techniques I would use with metal organic frameworks. So, no, like in Ireland, I've met some people who are working with MOFs. In Munich, there are people working with MOFs. A lot of publications from all around the world. So the community is great and one knows each other.
So for anyone listening in who's taking like an interest after hearing about this metal organic framework stuff,
yes.
What would they do if they wanted to start investigating this field themselves?
First of all, you should do chemistry studies. Shameless plug. We have here at Messi a really good and growing research group for metal organic frameworks. Shane Telfer, Professor Shane Telfer is my supervisor. He's the head of that. And we have all the equipment we definitely need for our research. So we have high-level X-ray diffraction. We have gas sorption. So we are like stacked out for exactly this part of research. And if you're interested, if you're interested in doing a chemistry study, there are summer internships you can apply for. And that's like, I think, the best way to have a first glimpse.
So stepping back a little bit, I'm also quite interested, because you made mention that this all started like 20 years ago. Perhaps you could tell the story of the genesis of metal organic frameworks.
It's quite funny because yesterday, or like today in New Zealand, there was the Nobel Prize in Chemistry.
Yes.
Which got awarded to nanodots. Cool research field. I'm not that familiar with it, but heads up to them. But one of the candidates for the Nobel Prize this year was Yagi, which is the father of metal organic frameworks. So he would have the Nobel Prize in Chemistry nearly went to metal organic frameworks this year. And Yagi, he designed the first metal MOF, which is called MOF 5. And yeah, like he literally designed the principle and the molecule, or like the framework, which doesn't really happen nowadays anymore because it just gets too complex. Usually, it's a finding in the lab, which was an accident. So you try to reproduce some data of another research group, and one of your compounds was kind of impure, and you suddenly get a shiny crystal in there, and then you go for the hunt for this crystal and get the structure with X-ray diffraction, and you're like, oh wow, this there's a different linker in there which I expected. So you like go further with that, and then like that's how most moths are found nowadays. Even though a lot of people say they still designed their moth. Yeah, it's more luck nowadays.
So it's kind of like throwing various things at the wall and seeing what sticks, so to speak.
Kind of, but like you still need the experience and the expertise to figure out what actually stuck.
Yeah,
which is the hard part, or well, a big part of it.
And the original one, as you said, was like one linker between between nodes.
One linker between metals, and based on that one, there were a huge series. They just experimented with what can you do with this one linker. So they attach different stuff on it. And the cool part about MOFs is, even if you attach stuff to your linkers, they usually still form the same framework, but like with stuff now attached to it. And yeah, well, that's quite some time now ago. I think it's like 35 years now. I don't have the exact date of the publication had. I should have, but I'm missing that right now. But well, this one is the most famous one, but it's not water stable, so it's not really useful for a lot of applications. A lot of different other moths just got found after that over the years, because it's a cool idea. You have something which is a solid, which is very open porous. You can like capture gases in there. You can do separation. You can do catalysis. It's versatile. It definitely is.
So what's going to be like the... So it sounds like that your research is like still in a state of progress right now, very deep within it. Do you reckon that you're perhaps... what would be like the key eureka moment for you?
Well, I think the key moment we had like 5 months ago.
Oh, it already happened, yeah, your key eureka moment.
Well, kind of.
Kind of.
Well, I hope there is going to be another one so it improves even further, but...
all right, well, how about go over what happened and then say what you... And then after that, elaborate on what you hope to happen next.
Yes. Well, my project is based on the research of a former PhD student who now works with the gas capture of the CO2. And he kind of did the proof of principle for that you can actually rip the catalyst and the chiral bit apart, put them on different linkers, and like you still get preferentially one of them. So my project started with a selectivity of one of the two mirror images of about 20 to 30%, depending on what like kind of system you had, which is already, well, it's 20 to 30%, so it actually shows that it works, which is a good starting point. And for the first 1.5 years of my project, I tried hundreds and thousands of experiments to see how to improve it, but 99.9% of them kind of like, gave the same result, or didn't improve anything, or like made the whole system not work anymore, which is just part of research. You need to do the experiments to see how to actually influence stuff. And about 5 months ago now, 4.5, we in the research group, we designed some new molecules, and one of my colleagues, she actually synthesized that one, and we share linkers because like we share information and stuff. So I attached it to got it to form my crystals, and got a really good first result. So I cooked it myself, and we improved the synthesis, got it in higher purity, put it into the MOF, and could increase our selectivity from about 20 to 30% to now up to 77%. So we tripled our selectivity.
Wow.
Yes, wow. That gave me a enormous boost of motivation, as you can believe or guess. And now we we got our hit. We tripled the selectivity, but now we completely switched our focus of our research to this kind of family of molecules. So we started with one, now we have like 15. So a lot of synthetic chemistry and putting them into our framework and seeing what happens, how we affect the selectivity with it. And we get a lot of valuable information over the last few weeks. So we are kind of in the stage where like, okay, we know those factors now. Let's kind of design the next stage of family, like the next series. And I'm starting my synthesis of that, like starting this week, which didn't work so far. Surprise, surprise. But it definitely will in the future. It's just a matter of putting in the hours. And then hopefully we get the selectivity from 77% up to 95%.
95, that is a big number.
Yeah, well, you have
big targets, say.
Yeah, big goals.
And so now that we're kind of looking forward here, what do you envision the future of metal organic frameworks to look like across the next 10 years or whatever time period you feel comfortable with?
Well, they will definitely get out of the stage of only university research into a lot of startups, and definitely also some bigger applications. My guess is definitely the major focus will be on the CO2 capture, because it's just such a important field of research with climate change and trying to reduce CO2 emission. So that one will definitely be one of the major applications of MOFs in the future, my guess. I hope that my research also finds the way into industry at some point. Definitely further down the line than 10 years, but yeah.
So currently there aren't any startups or companies like working on this? Is it just within university? Or?
Oh, no. As I said, we have a startup here in my research group, Captivate Technology.
Captivate Technology?
Yes. If you want to invest.
Do they work with Massive Ventures?
Yes, they work with Massive Ventures.
Cool.
And there are other companies out there, or like startups companies. I'm not that deep into that. Who also work with MOFs for CO2 capture, just using a different kind of MOF, because each MOF has its own like ups and downs. So ours is really, really selective for CO2. It's quite stable. It has good recyclability, and it's kind of low cost. But others maybe have some higher CO2 selectivity, and maybe some more CO2 fits into the pores, but it's more expensive. So it's like companies working with different materials, and let's see. I don't think only one of them will be applied in the future. I think there's going to be a mixture out there, not a mixture of MOFs in one system, but like different systems out there.
And do you think that there's a possibility you yourself might get involved with a startup?
I'm not sure. I personally don't see myself in academia in the future. I don't know. It's just a personal preference, I would say. So if it's a startup or a bigger company, I would not mind either. So maybe, yeah, why not?
Well, there you heard it. If anyone's looking for a future metal organic framework specialist, Ludwig Petters, he's got a CV hot on the table.
Well, give me another. Well, I'm studying my third year in November, so another 1.5 years, and then we can talk.
Some people they like to scout out that early, though.
Yeah, sure.
Because I can't imagine that there's a huge unlimited supply of people who are very experienced in your field.
Well, definitely not in New Zealand.
Yeah. I was wondering, so you talk about, carbon capture with these metal organic frameworks, using them for applications and stuff. What is like the life expectancy of a metal organic framework? How many times can you reuse it again before you might have to switch to some fresh ones?
Well, it depends on a lot of factors. First of all, the stream of air you put into your MOF. So if there's like a lot of sulfur-containing compounds or some other really aggressive like acids or whatever, it will definitely shorten the lifetime. Well, that's the reason. Like that's research that is done right now, or definitely the testing done right now for our system or Captivate technology system. How often you can recycle, but it's looking very, very promising. So like, if there is nothing like toxic in there, or like destroying, you can thousands of times.
Thousands of times. And how does this compare, I suppose, to conventional filtering technology that we have right now?
Well, conventional technology for carbon capture is often based on an amide solution. So it's it's a solutions-based system, and that one is relatively toxic. Plus, it's a lot of energy to recycle. You need to put a lot of energy back in there to get the CO2 out and to reuse your system.
And that's probably been the crux of it so far, is that you use so much energy that it makes you question, is it worth to spend this much energy which releases things to again take it out of the process?
Yes. You just need to do the calculations. Do I produce more CO2 using the energy to like remove the CO2 again, or is it actually like beneficial? Well, the big upside with MOFs is that, well, you can just apply vacuum, like a vacuum and temperature, and you get rid of the gas molecules usually. So it doesn't need a lot of energy for your regeneration, and it's usually very, very quick. So
you just kind of suck them all out again, and it's ready to have another go.
Exactly. You like industry usually works like that. So you have different columns, and one absorbs, the other one desorbs, and like where desorbs goes into a different like part of the factory. So you have like a very high concentration of CO2 then, and with that you can do chemistry again. Like CO2 is a like a lot of research groups work on that to use the carbon to actually make something valuable out of that. For example, methanol, or like even longer chained carbon sources for like fuels again.
Possibly even turning it into like plastic products or something.
Sure.
Yeah, I'm saying that because I did go to a conference that did talk about these things. So you've talked about how you're able to reuse, suck it out again, and then you said that it has. So you suck it out again, so you get like 1,000 goes of like sucking it out again before you need to like replace the metal organic framework itself.
Mm-hmm. Well, we hope that it's far more than 1,000. So,
okay.
Often if it's just like a you have water in your airstream and you slightly switch like decompose the framework, sometimes you can regenerate it with different techniques. So you don't even lose the your MOF, but well, I'm not that familiar with the whole project. It's not my major focus. It's just yeah.
So also more forward, even more forward looking. What is like your vision, like even further than the recent future? Like what would be like the long lasting effects of fully developing through this technology? Well, you can never really fully develop anything, but like going much further.
Well, the whole world is working towards like a CO2 neutral industry. So hopefully MOFs can do their part by capturing CO2 and then be able to use that again. So yeah, I hope the research in that field can do its part to that. But well, let's see if if the world achieves a CO2 neutral industry. That's far down the line, but well, I can't really talk about that, honestly.
Yeah. And you said that so you can capture out usable product of it. Is there a potential for this metal organic framework solution to be profitable to implement rather than a cost to offset the CO2 emissions?
Well, else there would not be startups if it would not be profitable. Well, you need to filter out the CO2, and you pay for doing so, whatever technology you use. So if you use the state of the art amide solutions, you pay a lot for like getting the solution, also for the recovery. There is definitely a cost involved for like setting up a system which is based on MOF carbon capture. Which one is more is better for the long run? I cannot tell because I don't know.
Yeah. It sounds like stretching you a bit thin there, because it's quite early stage, this technology still in many ways.
Well, and I'm not working fully with that.
Yeah.
Well, if people are interested in that technology, or like how the future will be, Captivate Technology has a website where you can like have a brief read about the technology itself, and if some investors are out there that are interested, like hit up my supervisor. He's definitely happy to have a chat.
All right. And asking you, are there any things that you would like to bring up in addition that I haven't been able to ask you?
Well, I was like very specific with metal organic frameworks right now. But chemistry is not only like that narrow. There are a lot of different like possibilities we have here at Messi. So sadly, the chemistry, like the whole science that here at Messi is like slowly in the decline. Probably all of you guys have heard about recent changes and proposals, but chemistry is still going, and we're going hard, and there is a lot of possibilities for future jobs you have as a chemist. So even if you're like completely overwhelmed with what I talked about the last time, there's or not that interested in like especially this research field, there are so many possibilities here at Messi, and well, I kind of just want to make a shameless plug for our university, I would say, because it's good here.
Yes, I think it'd be a great thing to have more people interested in participating in the College of Sciences here at Massey. Science is a fundamental part of our education system,
exactly,
and more people are always welcome.
Yeah.
That definitely was a definitely not a certain intention behind those words.
Yeah, we're all affected by changes, and well, I guess it's a lot. Still, like we suffer the aftermath of the pandemic a lot, with like students being missing for a long time, but. Yeah, no, it's a good university, and we have to keep the chins up, I guess.
Anyway, it sounds like we've gone through full loop on this conversation.
Yes.
So it's a pleasure having you here today. I found your expertise quite engaging. even as someone who's really not well acquainted with chemistry and often fights against it rather than working with it, I've definitely gained a lot of insight into these metal organic frameworks and their implications for society.
Thank you. I hoped I made it easy enough for everyone to understand, even though you don't really have a lot of basic, or like if you don't have a lot of basic knowledge about like the research field. I've been studying, 3 years bachelor's, 2 years master's, and now 2 years PhD, to be able to talk in that way about my field, and I'm still learning every day. So,
and what's some like this was quite a lot of higher level stuff, I would say. What's some good lower level resources for people to read on? So maybe when they think later after listening to this, they'll go, yeah, that's what it meant. I know you talked about the Captivate Technologies webpage.
It's the internet.
Yeah.
You find a lot of information about like all kinds of chemistry on there. If you really just want some basic knowledge, even though it's like not well like looked at, Wikipedia has a good basic impression. Like you get some good information out of that. You sure have to filter, and it's you definitely can't write a thesis or publication with that. But like for someone with no basic knowledge about that, it's a good start. And if you really want to dive a little deeper, for example, our research group has a intranet site where we showcase our MOFs with pictures, and you get to the publications of the individual MOFs, but that's already like deep down the road, kind of. So, I would say some YouTube, some Wikipedia. You will get some good information about that.
Okay, so if you want to drop some contact details again, in case you want to reach out to Ludwig and his team about metal organic frameworks.
If you want to reach out to me to like have maybe a chat, or like, I don't know why you would reach out to me, but it's l.petters, Petters @messi.ac.nz. The basic Messi PhD student mailing list. And if you would like to just have a look at my research group, Telfer Lab, it's called Shane Telfer, Telfer, is my supervisor, grad professor here at Messi University, and on his intranet site, you see our research group, our publications, and yeah.
All right. Pleasure having you, Ludwig.
It was a pleasure to be here.
So if you've also got an interesting story that you would like to share about your research and expertise, please send an email at martinallen111@gmail.com, all lower caps, and I can put you on the show yourself, and you can be sitting where Ludwig is sitting right now. Currently, it is 1:54 p.m. on a beautiful Thursday afternoon, and up next we've got the Kereru from Heavy Blarney. Enjoy.